Okay, guys. So we do have one last topic, and this is a topic that I mentioned before exam 3, and I said we'd be coming back to it. So there is a relationship between the cell potential, E naught cell, delta G, and K, the chemical equilibrium constant. Okay, so we're going to talk about what that relationship looks like. So delta G is equal to delta G naught plus RT ln of Q. So if I'm not under equilibrium conditions, I can use this to calculate how, which direction I need to move to get me back to equilibrium based on the conditions that I have, yada, yada, yada. Okay. A large negative value of delta G will tend to make G also negative. The reaction will proceed from left to right until a significant amount of the product is formed. A large positive delta G will tend to make the delta G also positive. Thus, the net reaction will proceed from right to left, backwards, until a significant amount of reactant has been formed. So again, when it's negative, it's going to keep going the way it's written. When it's positive, it's going to go the other way. Okay. At equilibrium, delta G equals 0. So Q equals K. So delta G naught equals minus RT ln of K. Because K is equal to Q at equilibrium. So that's where we get this relationship. So if I have delta G, I can calculate the equilibrium constant. If I have an equilibrium constant, I can calculate the delta G for that. Cool. Awesome. And one of the other things that you'll see, and I'm going to go ahead and get rid of this and move this back up so that we can take a better look at this. One of the other things you'll see is that there is a relationship between delta G, K, as predicted by that. So if K is greater than 1, then the natural log of K is positive, and delta G, therefore, is negative. So if K is greater than 1, we favor the products. So delta G has to be negative so that we can go forward to get those products. Okay. If K is equal to 1, then my delta G is 0. We're at equilibrium, so I'm not going forward or back. That makes sense. Oh. And if K is less than 1, then the natural log of K is negative, which makes delta G positive, which means K is less than 1. I have not enough of that reactant, so I need to make more reactant, and I do that by going backwards, which makes sense because if delta G is positive, I have to go backwards. Okay, so all of these things tie together. All right, so we can also say that we can add the E into this. We will at some point. So we can see, we go Q is greater than K. We have this delta G is less than 0. Those are spontaneous in the forward direction. Q is equal to K. We're at equilibrium. So we have no forward or backward movement. And Q is less than K. Our delta G is positive. We have to go back. Okay. So these are the same kinds of things that we were just talking about. Okay. Now, what else are we going to talk about? Okay, so I've asked that you calculate K for each of these using the delta G values that we'd already calculated. And we didn't actually calculate all of these values. So I'm going to put this on D2L so that we can see the practice that goes on with that. But again, if we were to talk about, I'm going to choose one of the delta G's we did calculate so that we can see what that looks like. Delta G. Okay, so we calculated a delta G here of negative 643.83. Negative 643.83. And that was kilojoules. And that's our delta G that we calculated for one of those reactions. Now remember that equation, which will be on the test, delta G naught is equal to minus RT ln of K. Now this one that we calculated, that was for 45 degrees C. Okay, so 318.15 Kelvin. When we calculated that, that's the value that we use for temperature. So if we want to be able to calculate our delta G, we can do that. We need to have the negative of R, which is 8.314, And joules per mole Kelvin, I think is what that actually is. Hold on, it's in here. 8.314 joules per Kelvin times mole. So that is on your test. And then T, which is 318.15 Kelvin. And then the natural log of K. So I can put in my delta G, negative 643.83. And that's going to give me something that I can simplify, which I will. I will have negative 643.83 kilojoules. I will divide that by the negative 8.314 joules per Kelvin times mole. And I will divide that by the 318.15 Kelvin. So the Kelvins will cancel. And then I'm going to have this problem because this is in joules and this is in kilojoules. So I'm going to convert this number to joules. So I'm going to take that negative 643.83 and I'll multiply that by 1,000. 643.830 joules. Okay. Then the joules will cancel, and that will leave me with a per mole value, which makes sense. Okay. And if I've moved all of that stuff over there, that means that's going to be equal to the natural log of K. Okay. So I'm going to simplify that value first because my head works better when I do it that way. So I'm going to divide by the 8.314. I'm going to divide by negative 318.15 because I didn't put the negative on the 8.314, so I'm putting it on this one. And that's going to give me that the natural log of K is equal to 243.404869. And again, I'm just leaving all the numbers that my calculator spit out at me. Now, if I want to get rid of a natural log, the way that I do that is to take e to the natural log of K is equal to e to the 243.404869. And that leaves me with K. These are the inverse of each other, so they cancel. So it's like taking 10 to the log kind of deal. So K is equal to this value. So I go second, e to the x, second answer. Dun, dun, dun. And it says it's huge. Air overflow is what I get. Okay. Which makes sense to me because you're taking E, which is a value that is, hold on, 2 point something, I think. Yeah, 2.718 is E. So you're taking that to the 243rd power. That's a huge value. Okay. So it's not capable of calculating that at that particular temperature. Okay? Sometimes this will happen. All right. So you may see that. Okay, we don't always have practical ways to use these equations to get to all the numbers that we want. Okay, so this is not unusual, but that's how you would do the math for that. Questions, comments, problems on that? Okay, I hope not, but again, that's how we would do that. And I think that will take us into our sample questions. So again, questions, comments, problems. I hope not, but if there are, let me know. Email, phone, WebEx, whatever. Hex-1-ene gas, C6H12, burns in oxygen to produce carbon dioxide and water vapor. Write an equation to represent this reaction. Okay, I have C6H12 burns in oxygen to give me carbon dioxide and water vapor. Carbon dioxide is a gas, water vapor is a gas. So I can look at this and go, right, I need 6 of those. So now I have the same number of carbons. That means that I then have 12 hydrogens over here, so I need to have 6 of those. That gives me my 12 hydrogens on both sides. And now I have 6 times 2 is 12, plus 6 is 18 oxygens, and so I need 9 of those to balance that. So that balances what I'm looking at. Cool. So that's my equation to represent that reaction. Use the data below to calculate the values of delta H and delta S. So we have an O2, a C6H12, a CO2, and an H2O. Okay, awesome. The first one is delta H. So delta H, delta S, which is not going to show up very well, but okay, we'll go with it. So my delta H for O2 is 0, C6H12 is negative 43, CO2 is negative 394, and H2O is negative 242. My delta S values, I have 205. Oh, sorry, wrong one, wrong order. 205 there. 385 here. My CO2 is 214. And my H2O is 189. Okay, so if I wanted to calculate delta H equals the sum of the products, sum of the stoichiometry of each of the products plus the sum minus the whole quantity sum of the stoichiometry times the values for my reactants. That sounds really bad. I hope you know what I meant. So my delta, and I'll just write it as the H is equal to the sum of the stoichiometry times the delta H, not F, for my products minus the sum of the stoichiometry of the delta H, not F, for the reactants. And of course, delta S is exactly the same. Delta G would be the same. Okay, awesome. All right. So delta H for this is going to be my products. So 6 times the negative 394 plus 6 times the negative 242. And I'm leaving the units off. I'm hoping that you can follow the units without me having to do it at this point. Minus the quantity of negative 43 from that first C6H2 plus 9 times 0. So 6 times negative 394 plus 6 times negative 242 minus the negative 93 gives me delta H equals negative 3723. And of course, that's kilojoules. And it's a per mole of C6H12. Okay, awesome. Well, that was fun. Now I can do delta S. And it looks so much like what I just did. So this time, I'm going to have the quantities 6 times the 189 plus 6 times the 214 minus 385 plus 9 times the 205. Okay, 6 times 189 plus 6 times 214. 2418. And then we have the 385 plus 9 times 205 gives me 2230. And so we take our 2418 minus the 2230, and that gives me delta S equals 188, and that's joules rather than kilojoules. So that's joules per Kelvin. Awesome. Calculate the standard free energy change for combustion of X1E. Standard means 25 degrees. So if I want to do standard, delta G is equal to delta H minus T delta S, or T equals 25 degrees C. 25 plus 273.5 gives me 298.15 Kelvin. So my delta H, negative 3723 kilojoules, minus 298.15 Kelvin times, and I'm going to take the 188, divide that by 1,000, 0.188 kilojoules per Kelvin. Multiply that by the 298.15. And that gives me negative 3723 kilojoules minus 56.0522 kilojoules. So I'm going to take negative 3723, add that. Subtract 56.0522. That gives me negative 3779.0522 kilojoules. Ooh, that was fun. Okay. State and explain whether the combustion of one hexene is spontaneous at 25 degrees. Would that be spontaneous? I say yes. I say it is because delta G is less than 0. So that's why I say that. Okay. What is delta G for the following reaction at 298? We have 2NH3 goes to N2 plus 3H2. We were given some values for that. So I want to calculate delta G. That's equal to delta H minus T delta S. My temperature is 298 Kelvin. The delta H that I'm given equals 92.4 kilojoules. And the delta S equals 198 joules. So I'm going to convert that 0.198 kilojoules per Kelvin. Okay. So I can plug some numbers in there, and that's equal to the 92.4 kilojoules minus 298 times 0.198 kilojoules per Kelvin. So times 298, and then plus, 92.4 minus that answer gives me a positive 33.396 kilojoules. Okay. So that's my value for delta G. It asked me to calculate the equilibrium constant for this reaction. Now, equilibrium constant. So I remember that delta G equals minus RT ln of K. So the delta G that I just calculated is 33.396. That's equal to negative 8.314, and that's in joules. .008314 kilojoules. My temperature at standard conditions is 298. And that's times the natural log of K. So I can take that 33.396. I divide that. 33.396. I divide it by that 0.008314. and I divide that by 298. And it gives me that the natural log of K is equal to 13.48. K is therefore equal to E to 13.48. So second E, second answer, and that gives me 714491 as my value for K. Well, that was fun. So now I actually got a value. It's huge, but I got a value. Calculate the equilibrium temperature for this reaction. So what I mean by equilibrium temperature is to find where that delta G is equal to 0. So if we want to talk about delta G being equal to 0, then remember that delta H is equal to T delta S. If I want to solve for that T, it's going to be delta H divided by delta S. We have values for both of those, so that T is going to equal 92.4 kilojoules over S. Oh yeah, 0.198 kilojoules per Kelvin. So 92.4 divided by 0.198. And that gives me that T for equilibrium is 466.7 Kelvin. Okay. So that's the temperature at which this would become spontaneous. And so that change in entropy would give me enough of a factor to be able to work with that. Okay. So going from the NH3 to the N2 plus the 3H2 becomes more of an issue over 466 Kelvin. Okay, awesome. Will product or reactant be formed above that temperature? So product or reactant be formed above that temperature, it'll become spontaneous. So product will be favored. Okay, so that's what we're talking about for that. Hopefully that helped. Now, these are calculations for free energy. I'm going to set them up for you, but I'm not actually going to calculate them. So my H2O liquid, H2O gas, where's my H2O liquid? It's not even in there. So I would have to look these up in those standard thermodynamic values. Okay, so it would be the H2O liquid minus the H2 plus half of the O2. So it's the H2 plus half the O2. That's the total that gets subtracted from the H2O. Okay, I'm going to do that on D2L because I need to look up those values because not all of them are here. Sorry about that. Questions, comments, problems on that? Okay, there is a free energy in-class worksheet. I'm going to pull it up over here so that we can take a look at what we got in that, just so I can talk to it a little bit. Example 3, free energy. This is the in-class practice. So again, we're looking to calculate the standard free energy change, delta G, for the following reaction. And I have delta G values for those. So that's delta G equal to the sum of the products minus the sum of the reactants. Okay. Reaction has a standard enthalpy change of delta H, 10 kilojoules per mole at 298. Standard entropy change, delta S, is 10 kilojoules per mole, It's the value of delta G for that reaction in kilojoules per mole. That's going to be delta G is equal to delta H minus T delta S. Remember that you have to convert your delta S to kilojoules because they want an answer in kilojoules. So make sure that you've done that conversion. Okay. The equation for the decomposition of calcium carbonate is given below. At 500 Kelvin, delta H for this is 177 kilojoules per mole, and delta S is 161 joules per Kelvin per mole. Explain why delta H for the reaction above cannot be described as a delta H not F. What does that delta, that not mean again? That means standard. So standard is 25 degrees, ambient pressure, 1 atmosphere, and we're making 1 mole of gas. So we have violated the temperature conditions for that. That's why it's not a delta H not F. State the meaning of the term delta S. Delta S is a measure of my entropy. Now, entropy, again, is a measure of the disorder in that molecule. So we're either talking about how free the individual molecules are to move against each other. So in a solid, they can't move at all. In a liquid, they can move against each other. In a gas, they're all over the place. So there's a lot of disorder there. But we also see that in larger molecules, there are more places that those subatomic particles can exist. And that creates additional disorder. So larger molecules have more places that they can be. We don't see that. The one place we wouldn't see that is in a single type of atom, like sodium, at 0 degrees Kelvin. So that would be an ideal crystal that has no movement because they're all exactly the same. So there's no distribution of the subatomic particles, okay? Calculate the value of delta G at 500 degrees Kelvin and determine, giving a reason, whether or not the reaction will be spontaneous. So delta G equals delta H minus T delta S. Make sure you do the conversion of this one so that it's in joules. And then based on the sign, you can predict the spontaneity. If it's less than 0, it will be spontaneous at 500 K. If it's greater than 0, it will be non-spontaneous and will only go the reverse direction. We can consider this reaction. Absolute entropy is given as for N2H2 and NH3. We want to calculate delta S naught for the reaction, explain the sign. Okay, so you're supposed to calculate that. The delta S for that, I would expect to be negative because we're going from 4 moles of gas to 2 moles of gas, so I would expect that to be a negative change, not favorable. We can calculate delta G for that at 238. And based on the delta G at 238, which is not a delta G naught, oops, calculate that delta G and state whether it's spontaneous or not based on its sign. So again, less than 0 is going to be spontaneous, greater than 0 won't be. Oh, we actually did this. We have already done this one. So that one is done for you. Yay, awesome. So that's what we're talking about. And there are answers for all of these. Okay. So you can consult with the answers to see whether you think there should be answers. Oh, yeah. So there are answers but down here. Okay. So that's everything for our Gibbs free energy. Now I am going to talk a little bit in a separate lecture about the lab final and what will be on that. And then I will talk a little bit about the final itself because I don't write that. So it's a little bit different than the tests you've already taken. Okay. At this point, as of today, which is 2:15, you will need to finish the materials for this exam. So thermochemistry, laws of thermodynamics, entropy in it, and free energy. You may or may not still have some labs outstanding. I know I still have grading to do for you. You may or may not have taken test 2. You'll need to take test 3. You will need to take the final, and you will need to take the lab final. So those are all of the things that are still outstanding for your grades. Now, again, you may not have done the calorimetry lab yet, and that's okay. You can do it after the lab final if you want to do that. There is some stuff on the lab final that is pertinent to that calorimetry lab, so you may want to look at that first, but that is entirely up to you. All right, guys, thanks for hanging with me. I will see you again for those last couple of topics, but I had a great semester. I hope you guys had a great semester, and I will get your grades to you as soon as I can. Thanks.